So, hello everyone. Today I'm going to explain about my first assignment based on statistics and the machine learning. So, today I'm going to cover some important questions in terms of interview. So, the first question is compute the Jacobian of the following transformation. So, here actually X and Y have been given. The X is y and the Y is actually x by y b square, x by y minus 4b square. So the Jacobian matrix, this is the actually the matrix from the Jacobian matrix. To find that, we have to calculate dx by dv, dx by d, dv and dy by dv and dy by dv. So let's find individually the dx by dv in terms of u. We have to differentiate the x. So the result is 1 by b, and the same to find the dy by dv, you have to differentiate the y in terms of u. So it's coming as b, and to get the dx by dv, so we have to find the x differentiation of x with respect to v. So it's coming as minus u by v square. And the dy by dv, we have to find the dy by dv also. So we have to differentiate the y in terms of v. So it's coming as a minus hv. And now simply we have to put all the values what we have calculated in the matrix form. So this is the final Jacobian matrix. So to simplify that, we are applying cross multiplication. So the result is coming as minus 8 plus c square v square. So let's jump into the next question. So it find out the inverse of the Trigonometric matrix that is given. So the matrix is 3 rows and 3 columns in present. So we all know the inverse formula. The inverse formula is 1 by determinant of A into adjoint of A. So, so to proceed with the inverse, we have to check the matrix is eligible to do the inverse or not. It is possible to do inverse or not. So for that we need to find the determinant. So let's calculate the determinant for the first matrix. So this is the like I have break down the steps. The first step we have to ignore the first row, and the first column, and we have to calculate for this second column, in the third row and third column. So the value is coming as 1 into 0 minus 6. And the second one, for the second term, we need to avoid this second column and the first row. So we have to calculate in the cross multiply in terms of 4 into minus 1 minus 0 into 6. So it's minus 4 minus 0. And for the last, we have to ignore this last column and the first row. So we have to apply we have to apply cross multiplication for 4, 1 and 0, 0. So the value is coming as 3 into 4 minus 0. So the overall value is coming as 2. So it's not equal to 0. So it's a non-singular matrix. So for any non-singular matrix, inverse calculation is possible. So let's proceed with this step. So, so to find the adjoint of the matrix, adjoint of the A, we know like to find the inverse, we need the adjoint of A. So to find the adjoint of A, we have to first calculate the cofactor matrix. So the cofactor matrix we can calculate by for each and every value in the matrix. So here is the I have visualized the for one value I have visualized the steps to find the cofactor. So here I have calculated the cofactor for 1. So I have ignored the first column and the first row, and I have applied the cross multiplication for 0, 6 and 1 minus 1. So the cofactor is 0 minus 6, 0 minus 6, so the value is coming as minus 6. And like that, we have to calculate for all the values for this matrix. 1, minus 1, 2, 4, 0, 6, minus 1. So accordingly, I have calculated and I have represented here. This is the final cofactor matrix. So this is not the final cofactor matrix. Actually, we also have to change the sign. It's a sign of the elements whichever actually present in the diamond shape curve, in the boundary of the diamond shape curve. Actually, these are the elements. For that, we need to change the sign. So here we have changed the sign. So this is the final cofactor matrix. So the adjoint, to find the adjoint matrix, the adjoint matrix is actually transpose of the cofactor matrix. So let's apply the transpose. So we all know like to find the transpose, we need to convert the rows to column and the columns to rows. So here the simply we have converted all the rows to column and the columns to rows. So if we minus 6, 4, 4 comes as the first column was minus 6, 4, 2, 3, 1, minus 1, the second row comes as the second column, 3, 1, minus 1. And minus 6 to 4 comes as the third row comes as the third column, minus 6 to 4. And now actually we are putting all the values in the formula. And after multiplying this one and a half into this matrix, the final result is this minus 3 by minus 3, 3 by 2, minus 2, 1 by 2, 1 and 2 minus half and 2. So let's jump into the machine learning part. So the first question is why is logistic regression terms of regression, not classification? So this is a very important interview question. So let's understand this. Why it is called as the regression and not classification? We all know in linear regression actually it predicts a continuous value directly. Like let's take an example. Like we are trying to predict the height based on weight for a man. So this is a regression, like it's a regression problem. And logistic regression on the other hand, it predicts the probability, which is then used for classification the two levels. Okay. So let's understand like how logistic regression basically works. So firstly, logistic regression starts by creating a linear equation like linear regression. So like this kind of example. So this Z is actually basically a continuous value, and this B0, B1 and B2, Bn, these are the coefficients. This coefficient can help the model to learn from the data. So after after actually creating a linear equation, we have to transform this equation into probability. So how can we transform this to probability? In this case, in terms of for logistic regression, actually this step can be done by the sigmoid function. So here actually to convert this continuous value to the probability, actually logistic regression use the sigmoid function. So here actually we are applying the sigmoid function. This is the formula for sigmoid function. So after applying sigmoid function, we are calculating the probability, and the function squares any number into the range of 0 and 1. So we all know the probability actually calculates the value between 0 and 1 and makes it interpretable as a probability. So after that, the part is the next step is the making a decision based on the probability. So the probability is used to classify the input. So for let's take an example. So if the probability is coming as 0.7, then we might decide it's class 1, and if the probability is coming as 0.3, like 30%, then we might decide the class is as 0. So a common threshold. So very first we need to define a common threshold. So here in this case, we have actually defined the common threshold as 0.5. So whatever value is coming greater than 0.5, then we are classifying it as class 1, and whatever values are coming less than that threshold value, those are actually we are classifying it as 0. So in summary, we can say as so logistic regression is called as regression because it starts by creating a linear equation like linear regression. So and the logistic part comes from the logistic function that converts the logistic function means the sigmoid function, you can take it as, and that's why that converts the continuous function to the probability. So that's why the logistic name comes as, and this is the reason that's why the logistic regression called as the regression or classification. I hope it clear. So let's moving into the next question. It is what is multicollinearity and how do you treat it and when it is not a problem? So this is also a very important question for interview. So what is multicollinearity? So multicollinearity occurs when two or more independent features are correlated with each other, highly correlated, you can say. So meaning they contain similar information. Like high correlation means what? Like they have similar information. They have the similar kind of information about the variance or in the dependent variables. So for that, the problem we can face as like when multicollinearity is present in the data set, it becomes too difficult to determine the individual effect of each feature on the dependable variable. So this can lead to unreliable and unstable estimation of regression coefficient. So let's discuss why it is a problem. So high correlation between independent variables can cause a large charges, uh, not charges, it's a large changes in a regression coefficient with small changes in the data because they have the similar data. So if the small changes in the data, then it could it could cause large changes in the regression coefficient and reduces the interpretability. So it becomes hard to interpretable, like which variable has the higher influence or like higher influencing ability to the dependable variable. Since they have the redundant data, they are similar kind of information, and also this makes it harder to determine if predictors are statistically significant or not. So when is multipolarity is not a problem. So when actually we are focusing on the more into the prediction part, our main goal is to prediction, not to see the relationship between the variables. Then we can take it as multipolarity. It might not be a major issue. So the model can still make accurate predictions even if the coefficients are not interpretable. If we are like more focused on the prediction, not interpretation, then we can ignore this multipolarity. So that is not a problem. So let's come into the like how to detect multipolarity. So we can detect the multipolarity by using VIF, variation inflation factor, a common rule of thumb. When the VIF is greater than 0, then the multipolarity is a concern. And also we can, I guess, detect it from the correlation matrix also. We can take the correlation between different pairs of the independent variables. If the if the values are coming high, close to 1 or -1, that suggests the multipolarity. So, let's discuss how to treat multipolarity. So, to treat the multipolarity, we can remove highly correlated weight sets, like drop one of the correlated variables from the model, or the combined model create a new variable that is a combination of those two highly correlated variables. Also, we can do principal component analysis, PCA, transform the correlated variables into a set of linearly uncorrelated variables. Also, we can apply regularization techniques, use the methods like Ridge regression, lasso regression, which add a penalty term to the size of the coefficient, thus handling multipolarity. So that's all. So this is an example. Also, we can discuss the example also. So let's take an example. So let's imagine we are building a model which can present the house prices. So we have two features. One is size in square feet and the number of rooms. So typically these features are highly correlated because larger house tends to higher number of rooms. So this multipolarity can make it hard to understand individual effects of each feature to detect the house prices. So this is the data. This is a dummy data actually. The correlation is like higher. It's 0.9 indicates multipolarity, and also the VI value is also coming as greater than 10. So we can also we can easily detect that this problem is a multipolarity problem. So to treat this multipolarity, the first approach we can take it as we can remove one variable of which means like any one variable we can drop to create this multipolarity. Otherwise, we can combine two variables and we can create a new variable that can represent both of the variables in one variable. And also we can use the Ridge regression. So this method actually can help the reduce the impact of multipolarity without dropping the variables, and Ridge regression can reduce the impact of multipolarity by penalizing large coefficient. Means it basically add the uh, the loss function, add the loss function for the penalty term into equation. That's why multipolarity can be handled by the Ridge regression. So let's go into the next question. Quickly explain hyperparameter optimization strategy. and optimization strategy performance. So we all know, like for hyperparameter optimization, there is a very big technique, one is grid strategy, and second is randomized strategy, and the third one is Bayesian optimization. So let's discuss one by one. So the first one is the grid search. So in this grid search optimization technique, it basically systematically search through a predefined grid of hyperparameter values. So it evaluates the model performance for each combination of the hyperparameters and selects the one with the best performance. So the pros is it's simple to implement and it can give the base hyperparameter within the specific grid. And the cons is computationally expensive because it takes one by one. It takes each and individual parameters under the data. So it is computationally expensive, especially when we have large such spaces. And so next is random search. So the approach is it randomly samples hyperparameter values from specific distribution. The process is like it's unlike not like the grid search. It does not try every of combination, but rather explores different regions of the search space. But basically, randomly it selects the combination and it calculates the parameters. So the pros is more efficient for a large search spaces and can often find good hyperparameter with clearly. And the cons is not guaranteed to find, like by using this, it's not guaranteed that it will give the best hyperparameter. But generally, in different cases, it generally often in practice. Like we can use this in terms of if we have large database, then we can random. So the last is Bayesian optimization. The approach is to use the probability model of objective function and uses this to decide which hyperparameter to try. And the process is balancing exploration, trying new hyperparameter, exploiting regional high performance, and the pros is efficient for expensive to evaluate function and adaptive search based on the past evaluation. So it learns from the past evaluation. So the concept is more complex to implement and requires tuning of additional parameters. Let's go into the optimization strategy performance. So grid search, it exhaustively search the entire search space. It go one by one and search and evaluate. So it guarantees to give the best. It can give us the best hyperparameter within the grid. So suitability, it can be suitable for small search space when when we have a small data set, where we can use different paper this search. And a random search is efficiently explores different region of search space. Basically, it find the randomly, it go randomly, and often find good hyperparameter with fewer regulation. So it can be suitable for large search spaces or when computational resources are limited, as it does not require evaluating all combinations. And Bayesian optimization, the performance is efficiently balancing exploration and exploitation, making it suitable for expensive to evaluate functions, and the suitable like it is suitable for cases where the objective function is computationally expensive or when the search space is complex. So overall, the grid search is simple but computationally expensive, suitable for small search spaces. Random search is efficient for large spaces, resource constrained environment, and the Bayesian optimization is efficient for expensive to evaluate functions and complex search spaces. So in summary, the choice of hyperparameter optimization strategy depends on the factors such as the size of the spaces and the computational resources and the nature of the objective function. So each strategy has its strengths and weaknesses. So the selecting most appropriate one requires consideration of these factors based on the data, based on the search spaces, based on the computational resources. So these are the main factors to choose the hyperparameter optimization technique. So that's all about today. So we'll meet on the next video. Thank you.